thank you very much for the introduction and for the invitation to give this talk. And so as the title suggests, we want to consider some system of equations. So let's take a fixed system of linear equations of this form here. So a homogeneous system of equations with zeros on the right-hand sides. And these coefficients, AJ, I of our equations should be in Fp. So here P is fixed and the system is fixed. And now for some very large n, we're interested in finding non-trivial solutions x1 to xk to the system of equations where these variables x1 to xk are going to be chosen to be vectors in Fp to the n. So the system is fixed, it's over Fp, and then we want to solve it in Fp to the n. And obviously solving it in all Fp to the n is very easy, but now naturally the question is we have some sort of subset A of Fp to the n in which we want to solve the system. And so a very natural extreme question is to ask what's the largest, so it's basically to ask how large do we need to make the set A in order to be able to solve the system, or to phrase this question differently, we can ask what's the largest possible size of a subset A of Fp to the n in which we can't solve the system. So we can ask what's the largest possible size of subset A of Fp to the n which doesn't have a non-trivial solution to the system star here. So here's again our system and the question. So we're wondering about the largest possible size of some subset A of Fp to the n without a non-trivial solution to the system star here. And so here we are asking kind of a characteristic P question. So we have coefficients in Fp and want to solve it in Fp to the n, but one can also ask the analogous sort of question when we take the coefficients to be integers, some fixed integers, and we want to solve it in a subset of 1 to n. And that problem, so it's basically the analogous sort of problem in characteristic 0, so solving it in subsets of 1 to n, is a very old problem which dates back many decades. And so, so in general, I mean, this is kind of a very general question, right? Taking this general system of equations, but there are also some very interesting special cases of this question. So for example, a special instance of such a question would be to ask what's the largest size of a subset of Fp to the n or the integers from 1 to n without a non-constant k-term arithmetic progression. So that sort of question would fit in this general framework here by taking k-2 equations and k variables which decode a k-term arithmetic progression. And as probably most of you know, I mean, this sort of question is one of the most fundamental questions in additive number theory. Or another kind of special case that has been studied is what's the largest size of a cdot set in Fp to the n or in the integers from 1 to n. So there we would only, in order to decode the cdot set, we would only need to take one equation and 4 variables. And then we could also ask basically this cdot set question in this general framework. Okay, so yeah, so here's again, so I hope I convinced you that this in general is an interesting type of question one can ask. And so here is again the question. We fix this system of equations with the coefficients in Fp, and we are now asking for the largest possible size of a subset of Fp to n without a non-trivial solution to the system star here. So here is first a kind of pretty easy observation. So suppose we are in the case that for one of these equations here in the system, these coefficients don't sum up to 0. So suppose that for some j from 1 to m, we have that aj1 plus and so on plus ajk is non-zero. Then it's not hard to see that there's a subset A of Fp to the n, which is very large, namely which has size p to the n minus 1, which is a 1 over p fraction of all of p to the n, so that there are no solutions x1 to xk at all in the subset A to the system star. So indeed, that's pretty easy to see because we can take the subset A of Fp to the n without any solutions just by taking all vectors in Fp to the n whose first coordinate is 1. If we take all vectors where the first coordinate is 1, then we won't be able to satisfy such an equation if aj1 plus and so on plus ajk is non-zero, right? Because then in the first coordinate, we would get something non-zero if we pick these x1 to xk in A and their first coordinate is all 1. So from this basically trivial observation, we can see that we can choose the subset A very large, namely basically as large as p to the n up to a constant factor of p is fixed, if we are in the case that for one of these equations, the coefficients don't sum up to 0. So that case is pretty boring, from that perspective at least. So from now on, let us assume that aj1 plus and so on plus ajk is 0 for all j. So in other words, let us assume that for each of the equations in our system, the coefficients do sum up to 0, because then the question we are asking becomes much more interesting. So here's again the question. So with this additional assumption now, that for each equation, these coefficients sum up to 0. And if we are in the, and so to remake this assumption throughout the rest of the talk now, and note that under this assumption that for each equation, the coefficients sum up to 0, we can now see that if we take x1 to xk to be all equal, so in other words, if we take x1 to xk to be x, and so on, x, for any x in A, we always get a solution to star, right? Because we assume that we have this assumption on the coefficients. So that's pretty boring as a solution, right? And that's in particular something we would certainly want to exclude when asking for a non-trivial solution. So, so here there's this word non-trivial, and I didn't tell you what I mean by this, but certainly we would want to exclude this case of the variables all being equal. So we can now, as a first question, ask, so what happens to the general sort of question we asked here, which isn't quite well defined because I didn't say what non-trivial is. What happens if we consider a solution x1 to xk to the system star to be non-trivial as soon as x1 to xk are not all equal? So as soon as we are not in this boring case here of x1 to xk all being equal to the same x. So if we allow all of these solutions where x1 to xk are not all equal, if we allow all of those to count as non-trivial solutions, we arrive at the question written here. So we have again the same system, the same assumptions, and now we are asking for the largest possible size of a subset A of fp to the n without a solution to the system where x1 to xk are not all equal. So that's now a well-defined question and an interesting one. And one piece to an answer was proved by Karl, Serra, and Wehner, and independently Shapira, who, well, to be more precise, they proved an arithmetic removal lemma for systems of linear equations, but in particular as a trivial corollary of their arithmetic removal lemma, one gets the statement printed here, namely that the largest possible size of a subset A of fp to the n without such a solution, where the variables are supposed to be not equal, must have size little o of p to the n. So in some sense, this theorem of Karl, Serra, and Wehner, and independently Shapira, tells us that the largest possible size of such a set A is small in the sense that it's little o of p to the n. And let me also point out that this is in some sense a very difficult result, because even though it's trivial to deduce it from this arithmetic removal lemma, and the arithmetic removal lemma, the pages, these papers are something like 10 pages long, but they do rely on kind of hypergraph regularity results. So in some sense, this is much deeper than it may look on the first glimpse. And also the quantitative bounds one gets for this little o of p to the n are very poor. Okay, so any questions to this point? Okay, so if not, then let me now mention that one can get much better bounds to this if one assumes that the number k of variables in the system is much larger than the number m of equations. So in other words, when assuming that k is sufficiently large with respect to m, then a result of tau gives much stronger bounds. Namely, so recall the previous bounds were just little o of p to the n with poor quantitative dependence, and the bounds that tau's result gives are that the size of A is exponentially smaller than p to the n, so much, much, much stronger bounds. And so here's this theorem of tau, so which says that if k is at least 2m plus 1, so k is sufficiently large with respect to m, then for such a set A without a solution x1 to xk to the system star where x1 to xk are not all equal, such a set A must have size at most gamma to the n for some constant gamma, which is strictly smaller than p. So note that if gamma was equal to p, this would be trivial, right? Because A is a subset of fp to the n. So A is at most p to the n, that would be trivial. But the point is that tau's result here gives exponentially better bounds than p to the n. And so here's again the same statement just written as a kind of theorem. So k is at least 2m plus 1. One has the system of equations with this assumption. And then the theorem says that there is a constant gamma strictly smaller than p, which only depends on p and the number m of equations here and the number k of variables. And the important thing is that the constant is strictly smaller than p, so that any subset A of fp to the n, which with size bigger than gamma to the n, this system has a solution in where these variables x1 to xk are in A, so that these vectors x1 to xk and A are not all equal. So this is this result of tau, and to be kind of very precise, tau hasn't written down this result exactly in this form, but it kind of follows immediately from what's now called tau's slicerank polynomial method. So so some historic remarks. So this builds upon a breakthrough of Kotlev and Pach and of Ellenberg and Reisweit on the problem of bounding the size of three-term progression sets, three-term progression-free sets in fp to the n, or in Z mod 4 to the n. That's in the case of the Kotlev-Pach work. And then after these works came out, Tau reformulated and generalized their proof method and introduced what is now called the slicerank polynomial method. And from this slicerank polynomial method, one immediately gets the theorem above, even though as far as I know, Tau hasn't written this down explicitly in this form, but it's really an immediate corollary of this method. Okay, any questions? Okay. So that gives a pretty good answer to the question we asked, at least assuming that k is sufficiently large with respect to 2m plus 1. If for this non-trivial here, we allow things as soon as the variables are not all the same. So in other words, this was our general question again, where we're wondering about the largest possible size of a subset of A of fp to the n without a non-trivial solution to the system. And so if k is at least 2m plus 1, then Tau's slicerank polynomial method gives a very strong upper bound on the size of A if for non-trivial it suffices for x1 to xk to be not all equal. But there are also various other notions of what we might want to mean by non-trivial, and there's kind of literature. So in the case of integers from problems in the integers from 1 to n, there's literature dating back more than 20 years ago by Ruja, who kind of studied various notions of non-trivial solutions and how they compare to each other. But so I would say a particularly natural notion one can consider, and that he also did consider, is if we demand for the variables to be all distinct. And this notion of non-triviality is also considered in other contexts often. So we can now ask the same question here, where for a non-trivial solution, we demand x1 to xk to be all distinct. And then the problem becomes much harder, right? Because Tau's theorem on the last slide, this allowed us to find a solution where x1 to xk are not all equal. But that doesn't give us that x1 to xk must be distinct. And that case is much harder. And in particular, the slicerank polynomial method proof completely breaks down in order to handle distinctness instead of just not all equal. Okay, so what the results I want to talk about in this talk are basically proving a result similar to Tau's result, where we replace not all equal by distinct. So we want to prove a bound similar to the one in Tau's result for the largest size of a subset A of fp to the n without a solution with distinct variables, where we again assume that k is sufficiently large with respect to m. So here we need to assume that k is at least 3m. And we also need to make an assumption that the system star is sufficiently generic. And so here is our theorem statement. So k is at least 3m. We have the system of equations. These coefficients are again in fp, and we make the assumption that for each equation, the coefficients sum up to 0. So we discussed before that this assumption is necessary to get anything interesting. But now we also need to make this genericity assumption, namely we need to assume that every m by m minor of the m by k matrix of these coefficients HIA is HAI is non-singular. So you have this matrix of these coefficients in the system, and we want to assume that all m by m minors are non-singular. And then the main result here states that there are constants c and gamma star, so that both only depending on p, m, and k, so that for every subset A of fp to the n of size larger than c times gamma star to the n, the system star has a solution in A, so that the variables x1 to xk are all distinct. And so again, the important thing is that this gamma star is strictly smaller than p, right? If you allowed gamma star to be p, this theorem would be stupid, but the important thing is that gamma star is strictly smaller than p. And so then having this sort of bound on the size of A suffices to find a solution in A to the system where the vectors x1 to xk are distinct. And so in other words, this tells us that if the system star satisfies the assumptions, then for any subset A without a solution with distinct variables, the size of A must again be exponentially smaller than p to the n. So again, that gives strong bounds for the size of such a subset A, which doesn't have a solution with distinct variables. Okay, and so let me also comment for a moment on this genericity assumption here. So on this assumption that these m by m minors of this matrix, this coefficient matrix here must be non-singular. So I want to point out that it's not possible to just remove this assumption from the theorem. So remember that in Tau's statement, we didn't have such an assumption, but here we can't just remove this assumption, because indeed, suppose that the equation x1 minus x2 equals 0 was either part of the system itself or was obtainable as a linear combination of the equations in the system, then clearly every solution to the system satisfies that x1 equals x2, and so in particular, there can't be any solutions with distinct x1 to xk. So clearly we need to make some sort of assumption on the structure of the system. So possibly this genericity assumption could be weakened. I'll say a bit more about that at the end, but certainly it can't just be removed. Okay, and also some historic remarks. So this main result here was previously known for the case where the system star is just the single equation x1 plus and so on plus xp equals 0. And that was solved by Naslund where it appeared in 2020. But in the journal version in 2020, but on the archive it was already in early 2017. And so this case is important because it's closely connected to the Erdős-Ginzburg-Sieve problem in discrete geometry, and that motivated Naslund to study this problem for this particular equation. And then for the slightly more general case of the system just consisting of one general linear equation with the coefficient summing to 0, but still just one equation, that was solved by Mimura and Tokushige. And then for multiple equations, some specific examples of linear systems were also the problem was also solved for those for some specific examples by Mimura and Tokushige in 2 different papers. But our result is the first reasonably general result on a wide class of systems of equations star. And so in the proof of our main result on this with this distinctness condition, we used combinatorial ideas as well as a probabilistic subspace sampling argument. But when we do subspace sampling, it's always important to kind of pay attention to, when we consider a solution x1 to xk to the system, what sort of the rank of the solution is. So what the dimension of the spans of the vectors x1 to xk in this solution are. So when you do kind of a probabilistic subspace sampling argument, when you take a random subspace, the probability that all of x1 to xk end up in the subspace is very much affected by what the dimension of the span is. If the solution is very low dimension, it's much more likely to end up in some random subspace than if it's basically high rank. So, and for that reason, we need so for that reason, in order to prove our main result, we need some sort of high rank generalization of Tau's slice rank method result in order to prove our main theorem. So what's written here is basically this high rank generalization. And it looks very similar to Tau, to this theorem following from Tau's slice rank method with the not all equal condition. The only difference is that here we talk about finding a solution to the system star where the dimension of the span of x1 to xk is at least r. So otherwise it looks the same as the other theorem. So we again, except that we now need k to be large with respect to m and r. So here we fix some r at least 2, where we want the dimension of the span to be at least r. So we fix some r at least 2, and we take k to be at least 2m plus r minus 1. We again consider such a system of equations with these coefficients in fp, so that for each equation the coefficients sum up to 0. And then we say that for every set A, which is large enough, where large enough again means of size at least c times gamma to the n for some fixed gamma strictly smaller than p, the system must have a solution in A where the dimension of the span of x1 to xk is at least r. And so this is indeed a generalization of this Tau result we saw before, because we can just take r equals 2 here, and then we immediately get a solution where x1 to xk are not all equal, right? Because if the dimension of the span is at least 2, then certainly x1 to xk can't be all equal. And so in that way, this can be considered kind of a generalization of this result for finding solutions with the variables being not all equal, but we also kind of get some sort of higher rank version of it, where we can take this dimension of the span to be at least any r.
So we have a question in the chat. Do we need r to be less than or equal to k?
Yes, so we need k to be at least 2m plus r minus 1, which in particular means that r is less than k. So we need k to be large with respect to m and r in this way written here. K is at least 2m plus r minus 1. Also, otherwise, I mean, if r was bigger than k, this wouldn't make much sense, right? Okay. Any other questions?
Are you going to talk about the discrepancy between 2k plus 2m plus 1 variables and 3m variables?
Yeah, so that discrepancy, I wasn't gonna say more about this, but that discrepancy basically just comes from, we wanna, in order to prove our main result about the distinctness, we will wanna apply this theorem with r being m plus 1. And that's the sole reason we need k to be at least 3m in the other result.
Okay. So, and I'm just thinking, because for Fourier methods, say saving a logarithm, one would expect to be able to prove these kind of distinct solution results with 2m plus 1 variables, right?
So I was going to say something in the concluding remarks on that. But yes, I agree with you that the distinctness sort of result should, in theory, also hold for fewer. I mean, one should expect it to hold for fewer variables, but the same actually with, I mean, one might also expect Tau's result to hold with fewer than 2m plus 1 variables too. So, yeah. Okay, so yeah, what I also wanted to mention is that proving this sort of high rank generalization of Tau's result is actually the main difficulty in showing our main result on the distinctness. So going from this theorem written here to this result on finding distinct solutions is actually not that hard, but proving this theorem is much harder. Okay, so for that reason, for the rest of the talk, I'll basically only talk about the proof of this theorem, and then one can get the other one, but with kind of, I mean, it's a bit of work, but it's less interesting, I would say, than the proof of this stuff. Yeah, so, okay, so let's talk about the proof approach to proving this theorem. And so again, here, if one wanted to apply Tau's slice rank method, the standard way of applying it doesn't work, because the relevant tensor one would have here is not a diagonal tensor. And so one can't just deduce this from Tau's slice rank polynomial method in the standard way on how one gets the result, the same way one gets the result with not all equal variables. Okay, so and so this fact about the tensor not being diagonal is actually a crucial problem, because as far as I know, all previous combinatorial applications of Tau's slice rank polynomial method have relied on the slice rank of diagonal tensors. And so here we will use a slice rank method for non-diagonal tensors. But in order to say a bit more about this, I should first make some definitions. So many of you have seen these definitions before, but let's remind everyone. So for L being at least 1 and K being at least 2, Tau defined the slice rank of a tensor. And so we first say that a tensor f from L to the K to some field f has slice rank 1 if it can be written as a product that f of L1 to Lk is always g of Li, so a function of just one of these variables here times a function h of the other variables. And so if we can factor f in this way, then we say it has slice rank 1. And then Tau defined the slice rank of an arbitrary function f from L to the K to some field f as the minimum number r, so that this function f can be written as the sum of r functions of slice rank 1. Okay, and so from this definition, it's not very hard to see that the slice rank of any tensor from L to the K to f is always at most L. And so typically when one applies the slice rank polynomial method to some combinatorial problem, then one chooses some tensor given by some suitably chosen polynomial expression that has to do with the problem. And then one uses a polynomial factoring trick, which first appeared in this work of Kohlhoff and Pach we mentioned earlier, in order to show an upper bound on the slice rank. So from the polynomial structure with this factoring trick, one gets an upper bound. And I won't go into the details here because I think many of you have seen this. But so then one has this upper bound on the slice rank. And in order for this upper bound to be useful, one needs to combine it with a lower bound. And so the lower bound is typically derived from the structure of the tensor. And so one way to do this is to use a lemma of Tau, where he showed that diagonal tensors have full slice rank. So diagonal tensor f from L to the K to f, which with non-zero elements on the diagonal must have full slice rank L. So that's what this lemma states. We have such a tensor so that when L1 to Lk are all equal, it's non-zero. So that means on the main diagonal, the entries are non-zero, but all other entries are 0, then the slice rank must be equal to L. And so as I mentioned, as far as I know, all previous combinatorial applications of the slice rank polynomial method have gone via this lemma for diagonal tensors. So they have relied on this lower bound for the slice rank of diagonal tensors. But as I also mentioned, in our problem, the tensor is unfortunately not diagonal. And so there have been other problems studied in the past with not diagonal tensors. So in particular, Naslund introduced some notion of partition rank to get around a similar sort of problem. But so that method also doesn't work in our case. And so then in the end, he again went via a diagonal tensor. But here we kind of, for the first time, find a combinatorial application that truly goes via a non-diagonal tensor. And so what we do is we use a lemma of Sauermann and Tau, which shows that certain non-diagonal tensors also have full slice rank L. And so here's the statement of this lemma. It's a little bit technical, but let me go through it slowly. Also, let me mention that very technically speaking, they didn't formulate the lemma in this way. They formulated some slightly more general lemma, but this is more an immediate corollary of the lemma that Sauermann and Tau formulated. So here the sort of lemma that we need now says if this k, so the number of variables we have here, so the set of 1 to k, where k is the number of variables, is partitioned into subsets j1 to jt, so that each of these subsets has size at least 2. And suppose now that f is some tensor, which again has non-zero elements everywhere on the diagonal. So f of L and so on, L is non-zero for all L. But let's also assume that for any choice of L1 to Lk and L, where the tensor is non-zero, so for every non-zero entry of this tensor, we have that we have for every h that the set of the Lj's with j and jh has size 1. So in other words, what this says, this is kind of a little bit hard to pass, but what it says is that if we take any non-zero entry of this tensor, so any entry so that f L1 and so on to Lk is non-zero. And then we look at any of these sets JH here. If we look at the corresponding L's for that index set JH here, then these L's are all equal. So for example, if we take just J1 and we take all Lj's with J and J1, these Lj's are all equal. And so we demand that this holds for any non-zero entry of this tensor F. Then the slice rank of F must be equal to L. Okay, so this lemma looks very technical, but let me first remark that it is a generalization of Tau's lemma for diagonal tensors. One can get this normal diagonal tensor lemma back by taking J1 to be, so taking the partition into just a single set J1, which is all of 1 to k. And then if one kind of thinks very hard about what this condition means, it means exactly it's a diagonal tensor in this case. But I mean, the lemma is more general because it allows for other partitions as well. But this generality, or this more general version for certain non-diagonal tensors, is unfortunately difficult to use in practice. So as I guess the statement is quite technical and hard to wrap one's head around. And so it's hard to find some sort of combinatorial setup where one actually is in the case of a tensor of this specific structure, if it's not a diagonal tensor. And so in our proof, we do manage to exploit the additional strength of this lemma for non-diagonal tensors by combining this with some complicated inductive setup and some careful combinatorial analysis to actually get us in the specific framework of this lemma. So unfortunately, the setup is quite technical, but I would like to give you at least a glimpse of how this works. So in the next few slides, I'll try to give an impression of how this works. I won't be able to explain all the details, but I just want to show you kind of sort of the rough definitions that, or the definitions that the setup works with, to kind of give you an impression of how roughly the argument goes. So in our inductive setup, we first need some, complicated looking definition. So what we say is that if we have a solution x1 to xk in FPN, where the vectors x1 to xk are all non-zero, to our system star, then to that solution, to any such solution, we want to associate a subset I of the index set from 1 to k with the following addition. So our associated set I for the solution should be so that the vectors xi for I and I are linearly independent. But it should be so that for any j outside I, xj is not in the span of these xi's. So this span of these xi's for I and I, so these vectors xi are linearly independent, but all the xj's with j outside I should not be in the span. And then there are typically many such sets I, where these conditions are satisfied, but among all subsets I satisfying these conditions 1 and 2, we want to choose the particular set I we associate to this solution so that it maximizes this expression here. So this expression counts k plus 1 times the size of I plus the number of, plus the kind of size of the set. And so let me just roughly say what this is. So for all indices j which are outside I, we consider the projection of the vector xj into the quotient space, where we divide the total space fp to the n by the space u, which is the span of these xi's. So u is the span here, and these xj's by this condition don't lie in the span. So this projection of xj into this quotient space is some non-zero vector in the quotient space, and then that means its span is a one-dimensional subspace of this quotient space. And so now this is the set of all one-dimensional subspaces of this quotient space fp to the n divided by u, which are of this particular form to be spanned by one of these projections of the xj's. And so we now count how many different such one-dimensional spans there are, right? Because we take the size of the set of one-dimensional subspaces. So in other words, the quantity we want to maximize here is k plus 1 times the size of I plus the number of different one-dimensional subspaces of this quotient space fp to the n divided by u that are spanned by these xj's, or by the xj projections. And So that's how we define a subset I that we associate with any solution x1 to xk. And now we define the weight of the solution x1 to xk to be the value of this quantity. So we maximize this quantity, and this maximum possible value is the weight of the solution x1 to xk. And so now it's not so hard to show that the dimension of the span of x1 to xk is always at least this weight divided by k plus 1. So that follows relatively easily from this definition. And so recall that our goal was to show that in any large subset A of fp to the n, we can find a solution to our system star where the dimension of the span is at least R. That was what we wanted to do. We wanted to prove this high rank generalization of this tau result. And so in order to do this now, to get kind of that the span is large, that the span is at least R, it now suffices by this inequality to get a solution where the weight is large. Okay, and so that's now what we want to do. So we want to do an induction on W, and for each W, we want to show that there's a solution x1 to xk in the set A to the system star, where the weight of the solution is bigger than W, if we assume that K is large enough with respect to M and W, and that the A is a large set. So the point of all of this is now that we induct basically on this weight. So we don't want to induct on the dimension of the span, because then we can't kind of get this to work. We need this complicated setup in order to be able to do some induction on this weight, because now the weight is chosen in a way that will lead us to a tensor of the specific structure we need for this Sauermann lemma. Okay, so now what's going to happen in the induction step? Well, as you may have been able to guess, is that we do proof by contradiction. So we assume that there is a large subset A of fp to the n, say without 0, so that all solutions x1 to xk to our system have weight at most W, right? Our goal was to show that we find a solution of weight bigger than W. And so in the induction step, we want to assume that all solutions in our large set A have weight at most W. Okay, and our goal is to get a contradiction. And so in order to do so, we want to perform again a probabilistic subspace sampling argument. So remember that we already wanted to do a probabilistic subspace sampling argument to get from this high rank result to our main result about distinctness. But here in the proof of the high rank result, we need yet another probabilistic subspace sampling argument. And so the goal of this probabilistic sampling argument is to get a subspace V of fp to the n of some suitably chosen dimension D. So we will choose V uniformly at random among all D-dimensional subspaces. And we want to get some large subset A star of A intersect V, so some subset A star which lies in B and is a subset of A, so that all solutions to star in the set A star have weight at most W minus 1. And if we have this, that all these solutions have weight at most W minus 1, then we can apply the induction hypothesis to A star and obtain a contradiction, right? Because by the induction hypothesis for W minus 1, it would tell us that if A star is large, then it would need to have a solution of weight bigger than W minus 1, and we get the desired contradiction. And here the important thing of A star lying in the subspace V, by the way, is so, is that we will kind of identify V with fp to the D and then basically apply the induction hypothesis to A star as a subset of fp to the D to get better bounds, or to get kind of the bounds that we need. Okay, so basically the main idea is we assume that in A, all solutions have weight at most W, and then the goal is to get some subspace sampling argument to get a subspace and a subset of that subspace, so that afterwards all solutions actually have weight at most W minus 1, so that we kill all solutions of weight equal to W. And then we should apply the induction hypothesis. So in order to do that, to get rid of all solutions with weight equal to W, we need to show that there aren't so many of them. So we need to show that there are only few solutions x1 to xk in our original set A, where the weight is equal to W. Or if we want to be more precisely, we actually have to show that there are only few solutions of any given rank, so of any dimension of the span of x1 to xk, because that again affects the probabilities for the subspace sampling. But let's not get into too much detail about the rank issue here. So roughly speaking, we want to show that there are only few solutions to the system where the weight is equal to W. And in order to bound the number of solutions with weight equal to W, that's where we use the slicerank polynomial argument with the Sauermann-Tau lemma for non-diagonal tensors in combination with kind of combinatorial arguments from the setup. And so the way we connect those two things is via the following lemma. So here's a lemma. If we have any solution in a to the k to the system star, and the associated set to the solution is some set I. So that was the definition we had before, how we associated the set I to each solution with these complicated conditions and the maximization of this complicated quantity. Then this lemma states that there is a partition of k without I into sets J1 to Jt, where each of these sets has size at least 2. And there are one-dimensional subspaces W1 to Wt of fp to the n divided by u, so of this quotient space fp to the n divided by u, where u is again the span of the xi with I and I. So this is exactly the quotient space. So the details the details are maybe a bit fast here, but the point is we again take the same quotient space that we did in this complicated definition earlier for associating the set I. And so in this quotient space, we now have that for every j outside I, this span of the projection of xj into this quotient space is equal to wh if j is in jh. So basically what these spaces w1 to wt tell us is if I take some index j and k without I, and I take this projection to the quotient space and its span, so that's now a one-dimensional subspace of this quotient space, this one-dimensional subspace is basically already determined by which of these sets J1 to Jt my little j lies in. So for each of these sets of the partition J1 to Jt, I have some particular one-dimensional subspace, and then if I take j in this jh, then the subspace I get by forming this thing is exactly this wh. So, and here kind of we already see some similarity to this Sauermann-Tau lemma, because here, there we also had this condition about the partition into subsets of size at least 2, and that's exactly what's happening here. And so, by the way, we applied the Sauermann-Tau lemma to k without I. And so I don't want to go into the details more here, but the idea is now that using the Sauermann-Tau lemma, we can now show that there are only few solutions x1 to xk in A to the system star, which have weight equal to W, and for which the sets W1 to Wt of these subspaces obtained in this lemma are disjoint. So basically, we can show that there are only few solutions with disjoint sets of subspaces coming from this lemma using this slice rank machinery and the Sauermann-Tau lemma. And so here, the important thing is that we need to verify the conditions in the Sauermann-Tau lemma, obviously, in order to apply the lemma, and verify. And so the way we will prove that these conditions hold is using our setup with this complicated definition of weight, and also the assumption that all solutions in A have weight at most W. So, I think this is kind of, the details are maybe too technical for the format of a talk, but the rough idea is that we have these spaces coming from this lemma, and now if we have a list of solutions where these spaces are all disjoint, then that defines a particular tensor, and now there can't be solutions which are across these kind of given list of solutions. There can't be any other non-zero, and there can be non-zero entries in the tensor which would be forbidden forbidden by the Sauermann-Tau conditions, because then they would need to go across in a way that those solutions would give higher weight than W. Anyway, I guess I think the details are too technical for a talk here, but I just wanted to give you a glimpse of how the way the argument roughly works. With analyzing basically this weight condition, and also this assumption that the solutions in A have weight at most W, one can then verify the conditions in the Sauer and Tau lemma, and then one can conclude from the lemma that first the number of any list of solutions where these subspaces W1 to WT, these sets of subspaces in the lemma are disjoint, that there can't be too many. And from that, one can then, with combinatorial arguments, conclude that the total number of solutions in A of weight equal to W is relatively small. And one can even do this for any given rank for the solutions. And so that will then allow us to perform the desired probabilistic subspace sampling argument that we said earlier we wanted to do. And so with the subspace sampling argument, one can then get rid of all solutions with weight equal to W. And from that, one can then apply the induction hypothesis and get the desired contradiction. So this is a very rough outline of how the proof for this high rank result roughly works. And so then our main result, so getting from this high rank result to our main result is in some sense less interesting. But also requires some work and some combinatorial ideas. But I would say it's less interesting maybe. Okay, so let me finish with some concluding remarks. So here's again our main theorem about these distinct solutions. So K is at least 3M, and we consider a fixed system of linear equations of this form, where we assume that the coefficients are in FP, where P is fixed, the system is fixed, and each equation in the system, for each equation in the system, the variables sum up to 0. And then we also have this genericity assumption, so that every m by m minor of this m by k matrix of these coefficients here is non-singular. And then this theorem states that there are these constants C and gamma star, where importantly gamma star is strictly smaller than P, so that for any subset A of Fp to the n of size at least C times gamma star to the n, this system star has a solution in A so that the vectors x1 to xk are distinct. And so as mentioned earlier, this genericity assumption here on this non-singularity of the minors of the matrix can't be completely removed. But I think it would be interesting to try to weaken this assumption. So here's again our system, and certainly we need the assumption we said earlier that each equation sums to 0. But now our goal is to try to, the goal could be to weaken the genericity assumption. But so note, we basically said this before, that if for some I which is not equal to I prime, we have xi minus x prime equals 0, either in the system or as a linear combination of the equations in the system, then the system can't have any solutions with distinct x1 to xk, right? Because this equation would always force xi to be equal to xi prime. So certainly if we wanted a theorem like the one on the last slide, so like this distinctness theorem, but with a weaker assumption on the matrix, we certainly do need to assume that the row span of this matrix does not contain any permutation of 1, -1, and 0, 0, and so on 0, right? Because otherwise, if it contains some permutation of this, then we can't have any solutions with distinct variables. And so that's, I think, this assumption and then this assumption about the row span certainly are kind of the minimum assumptions we need. And under these minimum assumptions, this arithmetic removal lemma for systems of equations of Carl, Serra, and Wiener and independently Shapira does imply that under these kind of assumptions, every subset A of Fp to the n without a solution to star with distinct variables must have size little O of P to the n. So that's already reassuring that these minimum assumptions imply that the size must be little O of P to the n. So here are again these assumptions. So the row span of the matrix shouldn't contain any permutation of 1, -1, 0, and so on 0. And each equation should have coefficients summing up to 0. Then I think it would be very tempting to ask whether under these weaker assumptions, basically, whether the statement in our main theorem still holds under these weaker assumptions. So one can ask whether under these weaker assumptions, one still has a bound of the form A is at most C times gamma star to the n for some gamma star strictly smaller than P, if A is a subset without a solution with distinct variables. Unfortunately, if such a bound is true, it would most likely be extremely hard to show, even if we assume that K is large with respect to M. So remember that in our theorem, we also had an assumption that k is large with respect to m, but even if you add such an assumption, this would be most likely extremely hard. And that's because showing this, even with the assumption that k is large with respect to m, would imply a bound on the form A is at most c times gamma star to the n with gamma star smaller than p for the size of a k-term progression-free subset A of p to the n. And this, I mean, proving such a bound for k-term progression-free subsets of fp to the n is certainly a very difficult problem that a lot of people have thought about in the last few years. I mean, especially after the Kreisweit proof for kind of the case k equals 3 came out. A lot of people have tried to generalize this to larger k, and it seems like everyone is stuck. So this is most likely very difficult. And so how would that follow from this? Well, if you as I guess many of you know, a k-term progression can be encoded by taking k minus 2 equations in k variables. And now if we just add one more kind of stupid equation with a lot of additional variables, as many as you want, then, and kind of very generically, then you would satisfy this weaker set of assumptions. I mean, as long as you take the additional equation to have coefficients summing up to 0, then you would satisfy this additional set of assumptions. But then if to that new system with k minus 1 equations, namely the k minus 2 original equations for the arithmetic progression, plus the stupid additional equation introducing a lot of new variables, then if you had a solution to that with all distinct variables, in particular, the original variable, say the first k variables from that arithmetic progression would give you a non-trivial arithmetic progression. So if you have, basically you add one equation, but you add a lot of variables, and then having all variables distinct in this big system would still give you that the first k things are non-trivial arithmetic progression. So for that reason, proving this main result under this weaker assumption is most likely extremely difficult. Yeah, but so that's all I wanted to say. Thank you.
All right, let's all unmute and clap and thank Lisa for a great talk.
Fantastic.
Okay, questions for Lisa?
Hi, Lisa. I have a question. So I saw you've worked with Jacob and Lassie on how to use these sort of results to prove arithmetic removal lemmas. So do you think that this new result you have would also imply a new arithmetic removal lemma of some sort?
You mean, say, for systems or something like that?
Yeah. Yes.
Yeah, so I don't think it implies it in any trivial way, but I've thought, I mean, I have thought a bit about whether one could use similar ideas to prove removal for systems under some, say, genericity assumption or so. And I haven't gotten, I haven't gotten it to work so far, but I mean, this work is very new. It came out last Monday, so maybe it does work. I'll think more about it. But certainly also for, if one wants to prove a removal lemma for systems with polynomial bounds, one should expect to need some genericity assumptions unless one feels confident enough to prove something about k-term arithmetic progressions, basically for the same reason as here. So if one proves a removal lemma with polynomial bounds for systems of equations, then it would in particular imply this sort of statement with the distinctness. And so because this would be hard without a bigger genericity assumption, it's most likely also very hard for removal for systems without a genericity assumption.
Okay.
Hi, Lisa, I have a quick question. Does your result give you a sort of accounting version of this, or does it follow from a standard Varnavini's averaging argument?
So I mean, so the proof doesn't give it. I'm not sure whether taking the result as a black box one can get. I mean, I guess you can kind of, okay, I guess you can probably get something by, say, use first sample a subspace, then apply the result, and then you might be, I mean, that will tell you that something about counting in the original space. But then again, it depends on the rank of the solution. So one has to be careful with these sorts of arguments. Yeah, so I'm not sure.
Yeah, I feel like that's sort of that type of result where you're sort of talking about the rank of the solutions is exactly the kind of thing that will be needed in an averaging argument to get a counting bound. So it's interesting that they're already phrased like that.
Yeah, but I mean, the rank result unfortunately doesn't say it's high rank. Well, I guess, yeah, I guess one could try to ask for something with high rank and distinct at the same time. Yeah, so yeah, I'm not sure. One would need to think about it for this precise sort of round.
Could ask another quick question. So in this Sauermann lemma on the non-diagonal tensor, the condition looks a lot like this notion of Rouja's of I think it's non-trivial solution, and maybe it's even how he defines genus.
I think it's a bit different, because in Rouja's non-trivial solution thing with the genus, what he does is he talks about so basically the partitions he is kind of basically taking there depend on the coefficients of the system, right? I mean, so you look at the coefficient of the system and then you split it up into sets where basically for each subset, the coefficients already sum up to 0. And then I guess you patch together your solution from kind of, I mean, that's how, somehow I think the idea between his non-trivial, you're muted.
Sorry, yeah, and then there's just one value for each part.
Exactly, yeah. Exactly. Whereas here, the partition is allowed to be anything, and here we are not talking about any system, right? We're just talking about a tensor. So in some sense, I guess in some sense it's similar maybe, but certainly it's not exactly the same.
Yeah, thank you.
But I've got one of those annoying comments more than a question type things. But I just want to say this minor condition that you have comes up very naturally when you do the Fourier analysis. And there, if you want to prove a density bound for these systems of equations with the minor condition, you can't encode longer progressions is what I'm saying. So for my impression, my naive take on the polynomial method is it seems to work when Fourier analysis works, and Fourier analysis works with this minor condition that your main density result has in 2n+1 variables. So I'm interested in closing that gap. I wouldn't let k-term progressions put you off, as it were, in closing that gap.
I see. So you're saying so you are not bothered by the assumption here about the minors, but you would like to see 2n+1 instead of 3n.
Yeah. I
think that would be interesting. I don't think the proof gives that, because one basically has to go via this rank result, and there one has to, I mean, in other words, there would be one way to do this could be to prove this sort of result with a better bound here, but yeah, I don't know. I mean,
thanks.
So Sean, just to follow up, so is it still the case that there is no complexity 2 or higher pattern that can be attacked so far by the polynomial method?
Well, as far as I know, no additional patterns can be attacked since basically your blog post came out. I mean,
okay. All right.
So another situation where this discrepancy in the number of variables is equations in squares. There's results on the polynomial method working for certain equations in squares due to bienvenue, but it's not as good as in the integers. Although
didn't Ben have something on that in that direction too?
Yeah, but there's with linear terms in those. Yeah. And Lisa, am I right in thinking that axis aligned corners haven't been tackled with the polynomial method? Is that?
That's true. I mean, that's correct as far as I know.
there's still no explanation as to somehow why the polynomial method seems to have almost the same limitations as the Fourier methods, because they have nothing in common otherwise. Yeah.
Maybe wrong, but I thought there were some complexity 1 systems that are not even amenable to the slicerank method, such as so if arithmetic progressions of rank 3 is 2 points on their midpoint, then 3 points on the 3 midpoints. I think I did the computation at some point, and I thought slicerank didn't give anything for this case, but I understand it to be complexity 1.
Right. Yeah, so it could even be a strictly smaller set of equations than the Fourier range. It's still weird. I do like how in this lemma of Will and I that you used, that the what you need to verify the hypotheses is almost the same as the output of the lemma, which is kind of weird, because the conclusion and the hypotheses of the lemma don't seem very related. So it's nice that you use the weight W hypothesis to get the hypotheses of the lemma, and then the conclusion gives you the weight W minus 1 control. I guess it shows that this lemma is actually kind of sharp. I guess that reminds me. So, I mean, the original Ellenberg-Gisbert result, I mean, it is sharp once you go to multicolored versions of the problem, right? I guess you have a paper on stuff like this. Do you expect something similar for these sort of results? That the bounds that you get, do you expect the exponent to be sharp once you suitably generalize?
Well, the first problem is that the proofs don't at all generalize to the multicolored thing, because you do this basically, at least the proofs in this paper all kind of don't generalize to multicolored, because you do the subspace sampling, and that's kind of bad with multicolored things.
Okay. Well, maybe a different question then. Do you like these numbers? So, you know, for the original approach, you know, the exponents that show up are so these have this natural entropy interpretation, and they kind of they seem sort of naturally associated with the problem. Like, do the gammas that show up in your argument, do they seem so canonical, or are they just some artificial thing?
They are artificial in the sense that you get artificial losses from the subspace sampling. So
okay.
you kind of do this induction, and you kind of lose at every step from the sampling. So it starts from kind of basically the natural thing you expect, but then you kind of basically at every step lose in an artificial way.
Okay.
Yeah, so maybe there's also some better proof of these sorts of theorems, which gives you kind of the gamma you would expect from the polynomial method without going through the induction and the subspace sampling. But yeah, this was I mean, as mentioned, it's kind of not so easy to tackle these questions just with polynomial method.
Yeah. It's a magic wand, which is, it's both very magic and very limited at the same time. It's